I'm gonna get started. Some people will come in, but hi everyone. Before I actually begin lecturing, do you have some general questions? Anything? Expectations? Demands about presentation style? No? You brought snacks. That's a great idea. Bring enough for everybody next time. No, I'm joking. No, it's yeah. If you want to cater this for everybody, that would be great. We could. It's a bit early, maybe for some of you, but yeah. Hi everyone. I'm Richard. This is Very Little Evolutionary Game Theory, which is just 5 lectures on evolutionary game theory. And I'm going to attempt to give you a tour of the foundational models in the evolution of social behavior, from conflict through families and societies. The course notes are already up online, a bunch of handwritten course notes and some typeset course notes on GitHub. If you go to github.com, and I am RMCELREATH. McElreath, yeah, rolls off the tongue. And then Very Little Evolutionary Game Theory in caps. And so the course notes are there for these lectures. There's some typeset notes with the mathematical derivations, and copies of my handwritten high-quality notes, right? Which I've discovered students really like to have these for some reason. But this is how I structure the lecture and plan it, so hopefully it's useful to you as well. So what are we going to do? Like I said, there's 5 lectures. The first lecture today is the evolution of conflict. Yeah, and then we're going to have 2 lectures a week. So it's Wednesday. Lectures are Mondays and Wednesdays. So Monday next week, I will give you the evolution of something not conflict, but the opposite, cooperation. And then in the subsequent lectures, we'll keep escalating the complexity of it. So we'll go to cooperation, we'll go into social groups and families and societies by the end. And then we'll have explained everything. Yeah, no. So these are short lectures. The goal is to do an hour and a half with you during each lecture. And not spend too much time on the mathematical derivations because, first of all, they're not that fancy. It's just basic algebra. But I'll give you some motivation in the beginning. And secondly, the course notes have much more detail about that stuff in them. And then there's a homework problem, exactly 1 homework problem to go with each lecture to help you practice and integrate what's in the lecture as well. And I think it's important to note that when you're learning game theory, you really have to do it. If I can just be in teacher mode for a second. So what does doing it mean? It means when you study it, you repeat the derivations and make sure that you really understand it. And then when you do the homework, you get to do something a little bit beyond the derivations. Yeah, so it's this analogy like if you tried to learn martial arts by watching Jackie Chan movies. Yeah, you're not going to learn a lot, right? You have to actually get out there and take some punches to learn martial arts. So that's sort of how it is with applied mathematics as well. You got to be willing to get in there and suffer a bit. No, but just a little, right? So, I've drained basically all the calculus out of these derivations, though, to make them accessible to everybody. And in the past, we've had good luck with that. So I think we will again. Any questions about procedures or anything before I start in? Okay, great. We'll reveal the other lectures as we go. So, what I want to get across most of all in this first lecture about evolutionary game theory, which is the study using applied mathematics of the evolution of social behavior, is that evolutionary game theory is incredibly stupid. The models we're going to study are really stupid. Like they're unbelievably simplified compared to the complexity of the social behavior that inspires the models. And this is obvious to everybody who studies animals or humans. Is that the models we're going to study are caricatures of social life. That said, as dumb as game theory is, it's not just evolutionary game theory, it's all of game theory, we are dumber. So we need this mental prosthetic of the simplified applied mathematics to reason through the consequences of simple assumptions. And that's the goal of this style of work and the framework for doing derivations. It turns out that our untutored intuitions are terrible for making inferences about these things. So you learn how to do this. You actually make yourself actively more intelligent at reasoning about these things by starting with toy models that are unbelievably simple, do incredible violence to the rich texture of animal life, but that's just necessary. That's how we do it. So when you have this flash of realization when I start driving the model that this is an incredibly stupid model, that is valid. I validate that reaction, but I want you to bear with me because you will still be surprised by really stupid models. It is hard to anticipate what actually happens in simple models of social behavior. And that's why the field is well known, because of those revelations, as it were. And today I want to focus on conflict, the evolution of conflict. The biological background for this domain of the study of evolution of social behavior is that biologists have observed that there is actually less conflict than they would have thought before. So let me set that up a bit for you in the natural history sense. Right? You might have thought like, that they thought like, why is there conflict at all? But that's not the history. The history works the other way, right? So you start out with nature is tooth and nail Darwinian idea. Of course things fight, right? There's finite resources. Not every animal can have, say, a nesting site or a carcass. So naturally animals fight. And we do see lots of fighting, sometimes quite lethal aggression in nature. Between species, but also within species. But naturalists have observed for a long time that often animals do not engage in lethal aggression. They resolve conflicts through some peaceful, so to speak, means like displays or just contests of staring, like who will leave first. Some sort of gamification of the resource struggle. And the question is why that should exist. And that's the inspiration, the historical origin of the models I want to give you a glimpse into today. It's the question of why is there so little lethal aggression, especially in species that are really good at dishing it out. So carnivorans like lions and tigers do fight with one another, but they are restrained when they do so. Much more restrained with one another when they fight than they are with their prey. Yeah, same is true of snakes and other things. Western rattlesnakes in North America, I don't know if anybody here has spent time vacationing in Western North America. It's a vast desert full of snakes. No, there are snakes everywhere in Western North America. Rattlesnakes wrestle when they meet one another. They're territorial and they wrestle. They have fangs. They can kill one another by biting, but they just wrestle for a while and it looks very strange. Yeah, with their prey, they do not wrestle. Right? They have a kiss that they deliver. Yeah, so this is the motivating thing. Why do snakes wrestle? You can think about this lecture as answering that question. Yes?
So we are talking about interspecies aggression.
The models I'm going to show you is the evolution of aggression within a species. Yeah, there's a very interesting set of questions about doing it between species too, and I'm not going to get to that with apologies, but it's actually nuanced because you can get between species cooperation and lack of aggression quite reliably in models as well. But the evolutionary dynamics are naturally different because of the gene pool and such. Okay, so the metaphor that this literature uses, and I think this is due to John Maynard Smith, like so many things in evolutionary game theory, is that we want to contrast two different strategies for resolving conflicts. And the first would be called hawk. Hawk is an aggressive strategy. We're going to imagine a scenario where there's some indivisible resource, like a territory, a nesting site, a food item. Two individuals contest over this resource, and an individual who acts like a hawk, has a hawk strategy, is willing to escalate to a potentially lethal aggression. Fighting over the resource. Consequence of hawk is that, of being a hawk is that you can get injured, right? You could deliver injury, but you could also be injured yourself. And I'm going to make these things more precise just in a moment. And the other sort of pure strategy to think about is something called dove. These are originally political science metaphors, right? Doves want peace, and it's a Cold War metaphors, but they predate the Cold War. So doves want peace, and hawks want a big military that deters aggression. Yeah, that's the idea. So doves hold out the olive branch, but in the biology models, doves don't just give up, right? Because they still want the resource. What they want to do is they want to resolve the conflict through some nonviolent means. But the conflict still exists. And the traditional view is like with the rattlesnakes, is there's some display, like wrestling. You may not think of wrestling as a display, but come on, it's on TV. Right, it's clearly a display. No, wrestling is a non-lethal means of conflict resolution. Now, it's been used like that. So the idea is snakes use it, so do people. Yeah, and dove is a wrestler. But the wrestling could be metaphorical. It could just be a display where the individuals don't touch. Lots of birds do this. They engage in displays. Eventually, one individual, for some reason, goes away. Yeah, we don't know why. The way we build an evolutionary game theoretic model of this is we imagine a population in which individuals have heritable strategies which lead them to behave in these different ways. And we're going to ask under what circumstances those heritable strategies can spread or go extinct. What are the conditions that favor hawks, and what are the conditions that favor doves? Are there conditions that favor both, so that we get a mix in the population? And I'm going to start with the dumbest game theory I can. Remember, I told you game theory is incredibly stupid. We're going to go right to the bottom of it, and we're going to think about completely pure hawk-dove types. And I preface this because you are smarter than the model at this point, right? I told you it'll be a stupid model, and you will recognize that, but wait, it could be continuous. I mean, you can be a little bit hawk, a little bit dove, yes. But I'm not going to start with that model, but we can do the continuous things. By the fifth lecture, we will be fully in continuous strategy spaces, all kinds of crazy stuff. I will take you there, I promise. I want to go there. But we're going to start with discrete, boring, incredibly stupid game theory today. And I just ask you to trust me that we will build these, layer in the complexity across the lectures instead of doing it all in the beginning. Just indulge me a bit. Yes, Christine.
Nonetheless, can I ask one question?
Of course.
Of course, so far we just look at heritable strategies with fixed payoffs here.
Yeah.
But I haven't found much literature, or actually no literature about as the point of the lethal strategies. For example, if models could control for that, the hawk dynamic would be a completely different one. The payoff would less fortunate for them, right? Mm-hmm. Are there models out there which control for that?
You mean have the lethal?
Yeah, for example, this is an aspect almost never considered because we focus on display here and it is quite discontinuous,
Yeah.
right?
Absolutely. I follow you, and let me get through the hawk-dove model thing, and then I'll answer your question, because then other people will understand what your question's about.
Great.
Yeah, but I completely...
It comes with me for a long time already.
Yeah. I completely understand your question, Christine, and it makes a lot of sense, but once I get the model presented, they'll know what you're talking... It'll be of more value if I answer you later. Apologies.
Yeah, I was thinking about to ask.
Yeah, it's good. that's good. Yeah, you're a little bit ahead of the class here because you've done this before. But okay, where was I? Yeah, we're going to make the model. So what we do is we posit that there are, again, it's incredibly stupid, there are alleles that make you, there's a single locus, and at that locus there are alleles that make you a hawk and alleles that make you a dove, and we're going to track the evolutionary dynamics of those alleles. There's a version of teaching this, like in the textbook that I wrote about this, where we do it with incredibly stupid popgen is what I'd call it. No, we actually, I show you that you can write down recursions for the allele frequencies and treat it like, baby's first population genetics model and do it all in that. In this lecture presentation, I'm going to do it heuristically and wave my hands a bit about those underlying dynamics, but I think you'll understand what's going on. But you can make it semi-credible as a popgen model. Yeah. So what we imagine, I just want you to think about, to make it easy, is we're going to start by imagining populations that are pure. So like everybody has the hawk allele, and I'm going to ask what happens when you become a dove, or a dove migrates in, or someone mutates into a dove. And then we're going to do the opposite. We're going to imagine a population that's all doves, and we'll ask what happens to the first hawk. And then we don't need to think about all the complicated population genetic stuff. We just need to ask what happens at the margin, and then I'll wave my hands about internal dynamics. No, we'll derive an internal equilibrium, but I want to go step by step. But it's easy enough to push all the genetics into the background and just think about consequences to begin with. So I'm going to define consequences now. So the first thing we need to do is talk about the value of the resource. And I'm just going to use the symbol V for this, the value of the resource, V for value. And this is some positive value in some fitness relevant currency. So it could be amount of food. This could be some multiplicative survival factor. It's a thing that benefits the individual's survival and reproduction. There would be additional expected number of offspring that it has, something like that. Yeah, so it's the value of holding the territory, eating the food item, acquiring the resource. And then, the other thing we need to posit is the consequence of getting into a fight. Or injury is bad, so there will be a cost of injury in this model, which I'll denote with a little c for cost. Again, this is a positive value. It's a positive cost. That may be it's a weird thing to think about, right? This will reduce the fitness of the individual, but it's a cost, right? So this is a positive value in the same units of currency as V. So number of offspring, survival probability, something like that. Good? Other models will have different symbols like this, and this is part of the creativity of this business in stupid model land, is you try to think about the story, the biological story, and reduce it down to this depleted world of a couple of Roman letters that encapsulate the whole struggle for existence. Yeah, that's our mission. And I want to show you that that's actually worth doing, and you can learn stuff from this. Okay, we're not going to pollute the board with more symbols just yet, but we just want to think about what happens with different kinds of encounters between the strategies we have already. So with simple game theoretic models, because they're so simple, we can represent the whole game with a little matrix. It's called a payoff matrix. And I'm going to draw one for you now for this game. And the idea is we write the names of each strategy along both sides of the matrix. In this case, there's only two, so it's easy. There's hawk and dove. And then the entries in this matrix are the consequences, the evolutionary consequences, to the focal individual, which is the individual on the row. Right, so put yourselves in the shoes of row player. You're over here, you're all important. Yeah, and this is the individual you meet. And we want to outline in this matrix the consequences of every possible interaction. For you, on the left, unconditional on what you are. Yeah, so we're going to write it down. So, or rather conditional on what you are. So if you're a hawk and you meet a hawk, we try to reason through what happens. So what do hawks do? Hawks are aggressive. They escalate to a fight. They bring out their fangs and their natural weaponry. If you win, so there's two hawks and they're fighting, one of them is going to win, maybe because it's more skilled, it's watched more Jackie Chan movies, whatever it is, right? But we don't know from the information in the matrix if that's you or the other one. So from your perspective, it's random, right, over evolutionary time. It's like a coin flip. Of course, in reality, it's not a coin flip because you watch Jackie Chan movies and you're more skilled than your opponent or something like that. But it's that your opponent could also have those advantages, right? And it's completely symmetric from that perspective. So half the time you will win. Does that make sense? I assert that. Of course, that randomness of it isn't actually random. We believe that there are deterministic reasons that one individual wins these contests, yeah? But we don't know that in this model, what those things are to determine who wins. And so instead we just say half the time you get V. This is the probability that you get that payoff. The other half of the time you don't win, you lose. And then you suffer the cost of injury. Yeah. And so 1/2, it's minus 1/2 C. So half the time you win, you get V. Half the time you get minus C. Yeah, you pay the cost. And because you're smart people and you're smarter than this dumb model, you're already thinking, but wait, they could both get injured and one could still win. Yes. And that's a great homework problem. That's the way I forget. I already posted the homework problem for this lecture, and maybe that's it actually, is to rederive the model under that assumption. But take a look. But we can talk about those alternatives later. And once you get a rhythm for how to do the model, it becomes easy to do those experiments yourself. You can change the way the model's formulated and derive things. Question?
Richard, sorry, this is probably really basic, but why is it a minus?
It's a minus because it reduces this individual's fitness. And so it's minus C. C is the cost of injury. It's how much it's reduced. So this is the change. Think about this expression as being the change in the individual's fitness. So there's a bunch of other stuff they're doing in their life that isn't this conflict, and they're accumulating survival, and lots of things happen to them. They survive things, they acquire food, they find some place to sleep, they find mates. And this is the marginal change in that because of this interaction, and so it can be negative. Yeah, even though fitness can't, right? So like 0 is an absorbing boundary in biology. Yeah, right, which is a thing that turns out to be important to Christine's question, actually, if we get to that. Yeah, question?
I know that it's mathematically the same, but would it also be safe to say that it is basically the value of the resource and you take out the cost of your injury, and because there are two individuals, you're just putting it as half because it's an aggregate?
Yeah. It's a good question. The evolutionary consequences on average are like that. For individuals, it's still true that you're either getting V or losing C, but the allele, from the gene's perspective, that's exactly what's going on, because the effects, the fitness consequences on the gene are spread across individuals in an evolutionary model. And if I did the whole PopGen model, I could show you that. And so from the gene's perspective, this is the expectation, this is the consequence to it, because there's a bunch of individuals that have the hawk gene. Some of them win, some of them lose. On average, they get this expression. But no individual gets this expression, right? Because either you win or you lose as an individual. Did that help? Was that your question, sort of? Yeah, so I think that's actually that's a super important thing about evolutionary theory, is that distinction between what happens to individuals and the distributional effects on alleles, which can be, sometimes the expectation is not all that matters. Variance matters a lot, right? The population geneticists know what I'm talking about. So we'll talk a little bit about that in a later lecture. Okay, are you with me here? Does this make sense? This is the hardest thing about that model, is deriving that expression. So we're done. Yeah. The others are easy. You're a hawk, you meet a dove. What happens? Well, you're willing to fight. The dove does a display or says, let's wrestle. And you're like, no, I'm going to kill you. And the dove runs away bravely. Yeah. So you get V. Yeah. It's no injury because there's no fight. The dove bravely runs away to live another day, but does not get the resource, and you do. All right, now we turn the tables. You're the dove now in that interaction. You meet a hawk. You say, let's wrestle. The hawk says, let's fight. So you run away. So there's no change in your fitness. Right? Now you might say, because you're smart people and the model is stupid, there's some display cost. Yes, and that's also a great homework problem. Right? There's some little display cost from like trying to do the display and then running away. And we can do that model as a bonus thing once we get the basic thing presented. But you get 0, and for the sake of clarity, when I write zeros, I'm going to put a little dot in the middle. Does that help people? Otherwise, it looks like an O, and my handwriting is bad enough as it is and doesn't need to get any worse. Okay. So this means no change. It doesn't mean you're dead. That's the important thing about this matrix. These are changes in fitness and not absolute fitness. All right, so this means no change. And then finally, a dove meets a dove. Now they both display, they wrestle. There's no injury. That's the idea. Unless something goes horribly wrong, there's no injury in the display. And then, again, there's some reason one individual wins the nonviolent contest, and it may be because they have more stamina, so they can display longer. There's interesting biological literature on that. But we're not here today to resolve that, because this is a stupid model. Instead, we're going to say, what are the consequences? Whatever the mechanism is, we're going to represent those consequences distributionally in terms of payoffs. And so, you win at random. Just like as if it was 2 hawks, one individual wins at random, but there's no injury cost here. So half the time you get V, and half the time you get 0, right? So this is winning and that's losing, just like in the hawk expression, but there's no cost here. So this is just half V. It's still, the resource can't be divided, is what we're assuming. Yeah, and yes, you can make a version of the model where you divide the resource, and it's very similar, but once I teach this to you, you'll be able to do this all night long, do versions of this model where you change the resource a little bit. Does this make sense? So with simple models like this, these matrices are really useful because we can, with our eyes almost, just derive the consequences evolutionarily by looking at the matrix. And I want to show you how to do that. And we're going to think about pure populations to start, and we're going to ask, in a world of hawks, if the first dove, or what are the circumstances that the first dove could get an evolutionary foothold? Or to be more precise, under what conditions would natural selection favor a rare dove? Okay, we're going to ask this formally in a second. We're going to use the expressions in the matrix to do it. And then we're going to flip it, and we're going to ask in the dove world, what circumstances favor a rare hawk? And then we'll move on to something more nuanced than that. The way we think about that is, in the all hawk world, this is the way we're going to express it, is when is hawk and evolutionarily stable strategy, right? Or ESS, right? When is hawk an evolutionarily stable strategy? And what that's going to mean is, what this always conventionally means, is that hawk is common, and we introduce some rare competing strategy, in this case dove, and we ask if that rare competing strategy can increase. If it cannot, then hawk is evolutionarily stable. It is rare invading alternative alleles cannot increase under natural selection. Yeah. They could increase under mass migration or other evolutionary forces that we don't have in the model, but we are isolating down to asking, what would natural selection do if it had its way? All the biologists know that in real nature, natural selection doesn't always get its way, because genomes are interesting, right? Phenotypes are controlled by a huge number of different loci. To a first order approximation, your entire genome is responsible for every phenotype, right? So that's sort of my basic view of what we've learned from the genomics era. Right? This model is on the other end of that, right? Absolutely. But logically, it's like a little calculator to help us understand if natural selection did get its way, what would it do? And that doesn't lead us directly to predictions, but it gives us insights that we didn't have before we started the model. That's my promise, okay? So you can decide for yourself. So how do we ask that? Well, first we say, what is the average fitness? What is in the hawk world for the hawk allele, right? That gives us what the invader has to beat. So that's where we start. And that's thankfully easy, because when you're a hawk and hawk is common, you just meet other hawks. Yeah? And yes, we're going to see in a moment, there's this one hawk that meets the invader. We're going to have an invading dove that we throw into the arena. And one hawk will meet that dove. But the hawk allele, whatever the genetic architecture is that makes an individual a hawk, is determined almost exclusively by interactions with hawks when it's common. So that makes the calculation easy. Does that make sense? So, I'm going to introduce a bit of notation, right? We're going to say capital V when hawk meets hawk, right? So the change in fitness to a hawk, conditional on meeting a hawk. This is notation I use this notation in the notes, and I'll use it across the lectures. It saves us some writing time, yeah? So this is the change in fitness for a hawk, conditional on meeting a hawk. This is what you get in when hawk is common, is V minus C over 2. Yeah, that's the expected average evolutionary consequences when hawk is common for a hawk. And we need to know if the rare dove can do better than that. When dove is rare, just to pay off to dove, it's only meeting hawks. There isn't another dove. Yeah? And so we want to know the change in fitness to a dove conditional on meeting a hawk. You with me? Does the notation help? Yeah. And that is 0, right from the matrix. And so then we just ask, using these expressions, the condition for an ESS is that V minus C over 2 be greater than 0, right? That hawks, when common, have higher fitness than the rare dove. And that's what this expression is asking. It's a question. Yeah, it's an inequality, but it's a question. And so then we just need to algebraically reduce this until we get the answer. So I appreciate, usually when I start this course, some of you, all of you have done algebra, but maybe it was a long time ago. It's an old friend of yours. And so for the first couple of lectures, I'll do some derivations. Yeah, just to warm you up and bring back that warm glow you had when you did algebra. Yeah? And then it'll all come rushing back, and you'll remember the sweet release of solving algebra homework problems, right? And it will come back to you. In the later lectures, there just won't be enough time for me to do all the derivations, and I'm going to skip some steps, but you have the notes, right, which has everything in it. And of course, if you ever have questions, I will pull out paper and do the derivations with you, okay? Let me do this one for you. Just a few steps. We have V minus C over 2 greater than 0. We can get rid of the 2, right, by multiplying both sides by 2. So we get V minus C is greater than 0. And then I'm just going to move the C over by adding C to both sides. And so the condition is that V is greater than C. Now it's our job as creative analysts to interpret this, given the definitions we chose for these variables. So in this case, the question is, when is hawk an evolutionarily stable strategy? And the answer is when V is greater than C, when the value of the resource exceeds the cost of injury for escalating. Which maybe in hindsight is like, well, of course. And that is the sensation that you should get with all these models. Even though probably you couldn't have predicted that this is the condition ahead of time, it is it must be always a direct consequence of the assumptions. It's just that, people aren't very good at knowing the consequences of assumptions without doing the work. And that's what we're doing here. Yeah, question?
Could you explain 1 second why we arrived at the inequality to answer our question? Why it should be greater than?
Because an evolutionary stable strategy is one that has higher fitness than invaders. So this is the statement. This is the fitness of hawk when it's common. This is the fitness of the invader. So this is the algebraic version of this question about being an evolutionarily stable strategy.
So we are just equating fitness with the outcome, right?
Well, we don't know where in a moment I'll diagram this for you. I would say no to the way that was expressed. This is only at the margin. We don't know what happens in the long run evolutionarily here. We're just saying, can a rare strategy increase? That's all we're asking. We don't know what happens to that rare strategy after it increases yet, but we're going to go there in a bit, okay? If that's what you were asking. Yeah, we're just at the edge and we're saying, put a dove in there, does the dove increase in frequency? Could it possibly increase in frequency, or will it get pounded? Right, and that's the question. And the condition is V greater than C. So if V is greater than C, dove does not invade through natural selection. It could invade through drift. Selection could be super weak, and drift could dominate. There could be migration. So dove could increase under other forces that aren't in this model. Right? I never mentioned drift here. I haven't mentioned migration. I haven't said where this rare dove comes from. Right? Yeah. This is just to say comparing the fitnesses with natural selection, if it's got its way, increase doves. And if V is greater than C, no. Hawk is an ESS. Does that make sense? And maybe it makes some sense because if the value of the resource is greater than your cost of injury, you should go for it. That's what the math says. Yeah. Christine.
But just a question. Is drift not considered in this model somehow by the change in fitness? I mean, if there's no change in fitness, we assume drift. Also I thought actually neutral drift can be included even in this model.
Well, we're going to wave our hand. I'm going to wave my hands about drift in a little bit because I'm going to talk about retaliator, and then there's drift dynamics that we have to talk about with retaliation.
Just by the payoff metric.
Exactly. So that's where I'm headed. Exactly right. Okay. If, however, V is less than C, if this is not satisfied, then the rare dove can increase. And then we want to think about that counterfactual as well. So so let's say hawk is ESS when that's true. If that's not true, a rare dove can increase. And why? The rare dove is never winning, remember. The rare dove never gets the resource. How can it increase in frequency? It can increase in frequency because the hawks are killing one another, right? I mean, in this model, they're not killing one another. They're just paying some cost, C. But if C is greater than the value of the resource, then the contests are really bad. They're essentially wasting the value of the resource from a pure ecological dove perspective, right? It's like, come on, guys, can't we get along? We could peacefully resolve this. We're basically burning up the value of the resource by injuring one another, yeah? But we've all been in that classroom, right? Where that happens. So you recognize this can happen. Does that make some sense? So you think about it in both directions. Now, let's consider doves in earnest. When this rare dove increases, maybe there could be a world that's all doves. So we're going to ask the symmetric question, when is dove an ESS? ESS. And to ask that, we're going to have an inequality just like this, but what's on the left is going to be the payoff to doves when they are common, because that's what the doves are getting. And the rare type has to beat that. And now the rare type is going to be a hawk. So let's think about it first. What does a dove get when doves are common? And you can take it straight from the matrix. Let your eyes wander the payoff matrix there for a moment and find the payoff that a dove gets when doves are common. Have you found it? Yes, you burning your eyes into it? Yes, okay. It is here. Yeah? And I'm going to write that as V over 2. Okay? 1/2 V. And that must be greater than, for dove to be an ESS, that must be greater than what a rare hawk gets. Now again, use your analyst eyeballs on the matrix and find, yeah, I apologize for this, but you get good at this. And I'm going to draw a bigger matrix in a moment, so you want to get used to looking at the matrix. You're going to wander, right? So it's V because the rare hawk always wins. Yeah? The doves have never seen an animal like this before. They're not sure what to do with it. They just run away, and the hawk wins. Now, algebraically, we could have some fun with this, but I think you can probably see what's required for this to be satisfied. Yeah. Think about it for a moment. There is a situation in which this can be true, and the answer is when V is negative. Yeah. I'll let you focus on that for a moment. This is not satisfied under the story that justifies the definition of the variable, right? The animals are not fighting over something that hurts them, right? You've met those people, though, right, who'd fight over things that will do damage to them. but that's not the model we're making here, right? That'd be an interesting homework problem again. But in this case, we're assuming V is positive, and so this is never satisfied. Dove is never evolutionarily stable. It's always can be invaded by rare hawks, meaning that a rare hawk will increase in frequency under natural selection. Good? Okay, so let me summarize what we've done so far. I want you to think about the population as like a line segment where we chart out between all dove world on one end and all hawk world on the other. In other words, this line segment is the frequency of hawks in the population. Yeah, I mentioned large populations, a bunch of individuals, we could genotype all of them, and we put down the frequency of hawks after genotyping. It would be somewhere in this space between 0 and 1. With me? Yeah, and we can assign a symbol to this like, P, which is the proportion of hawks in the population. Yeah. I think I use P in the notes. So what we've looked at so far are just the ends of this line segment, right? There's a bunch of evolution dynamics that can happen internally here. Yeah, what would natural selection do at any particular frequency of P is something we often want to know. We've started here, and we said, if we're here and we move ourselves in just a little bit, we add one dove, what does natural selection do? And the answer was, well, it depends. If V is greater than C, then you go right back up, right? Because the rare dove can't invade. So imagine that world for a second. We assume V is greater than C, and then the evolution dynamics there are when hawks are common, is that the evolution tends to take you back to pure hawks. Yeah, and again, other forces like continued migration, strong mutation, other things could keep you internal here, but we're just asking what natural selection does. At this end, it doesn't matter if V is greater than C or not, you always move up, right? Rare hawks increase. Yeah? Remember, rare hawks can increase even when contests are dangerous, when C is large, because they're not getting injured when they're rare. Right? Or they're only rarely getting injured because they're meeting doves most of the time. So they can increase when rare. Or another way to think about what we've derived so far is, let me draw the other version of this and then it'll make more sense. So this is the V greater than C world. The V less than C world is different. So still, those are terrible arrows. There we go. All right. So still rare hawks increase, but when V is less than C, rare doves can also increase. So this is one evolution dynamic where inevitably the world is all hawk. Rare doves invade. Rare hawks invade, rare doves don't. But if V is less than C, something happens in the middle here, right? Because rare doves can increase and rare hawks can increase. You with me? This is like the two different dynamics that this model can produce. Just terrible hawk world because injury is not serious enough to discourage aggression, or this case where doves can increase when rare because they're avoiding injury, because injury is dangerous. I mean, that's up here, sorry. Hawks can increase when rare because they're not getting injured yet. And the problem with hawks in this regime is they can't live with one another. They can invade when rare. They're a strategy that does really well when they don't meet themselves. But in evolutionary game theory, a theme will develop across the lectures that strategies that do not live well with themselves are not great candidates evolutionarily. Yeah, I'll say that again. Strategies that cannot live well with themselves are not great evolutionary candidates for behavior. It's a basic problem if you're increasing in frequency and you can't get along with yourself. This is a setup for a bad time. Yeah? Doves get along with themselves very well. They efficiently divide the resource without any conflict. Well, some wrestling or whatever, or coin flip, however you want to decide it's done, but they can't be stable. So this is the basic setup in this model. You with me? Yeah, these are both bad strategies. I told you it was a stupid model, right? We're going to add a third strategy in a second, and I think we've got time today to talk about that. Yeah. Yeah, we're right on time.
In the model would also be less than C. Is the probability also probability of hawk?
Yeah, it's all the same, exactly. So this dimension is still the frequency of hawk. Yeah, these are the same diagram, but with different dynamics, depending upon whether the V is greater than C or V is less than C. We could draw it the other way, if that's the question. We could draw this as the frequency of dove, but we just need one symbol for both because there's only two types. I'm going to add a third strategy in a moment, and then we're going to need another axis. And I'm going to redraw the evolution dynamics with 3 strategies, and that'll be fun for me. I don't know about you. But, did I answer your question? Is that, yeah, okay. Question?
When weight is less than C, because we're still talking about the probability of hawks, why would it move towards the doves? Like, are we saying that it moves more towards a display?
We haven't, I'm going to derive where it goes, and then I think your question will be answered. But doves are never in ESS. So that's why hawks increase when rare still. So that's always true. The only thing that's different when B is less than C is what happens on the high end here. And something's got to happen in the middle because doves increase when rare, and so do hawks. So what happens as when they're both common? Yeah, are they gonna, and lots of things can happen. This is what we're gonna do next in evolutionary models. So you can have, and this is a stupid model, so nothing exciting is gonna happen, but exciting things can happen in evolutionary models. You can have endless cycles, you can have one driving the other extinct. There's lots of really cool ecological things that can happen under mixtures of different types when they compete and cooperate. In this model, what's going to happen is there's going to be some internal frequency of hawks and doves under which selection is effectively neutral, meaning when you're close to that particular mixture of hawks and doves, say 2/3 hawks, 1/3 doves, we'll derive an expression for it. Selection doesn't tend to increase either. And so selection becomes effectively neutral in that zone. And this is what's called an equilibrium. Yeah, a mixed equilibrium. And I'm going to derive that. It's going to be somewhere in here. There's going to be some point at which some mix of hawks and doves or some frequency P, some value of P that we're going to derive, under which if you added hawks to the population and moved yourself this way, natural selection would tend to move you back to that point. And if you added doves, natural selection would tend to move you back to the point as well. And we're going to derive that mixture now. Okay? Yes. So now I need to erase stuff. Let's start here. Okay. So how do we do that? Ooh, there's water. All right, so P is the frequency of hawks, and what we want to do now is this thing of saying what is the expected change in fitness of a hawk in a population in which they can meet both hawks and doves? And we're going to write an expression for that. Now, I've just erased the payoff matrix, but I know it's in your notes or in your mind forever. And so we will summon it from your memory now, which I've done this deliberately. It seems like a teaching mistake, but oh no. No. This is a chance for you to re-derive the matrix in your mind or from your notes and re-access it without just looking at the board. But we're going to write this expression, right? So the idea is, what is the change in fitness of a hawk when it can meet hawks and doves? And the way I write this in the notes is we have some fitness expression, capital W, which is often used in evolutionary theory to indicate fitness expressions. I don't know why. It's just historical. Nobody knows an answer to this. So the fitness of hawk in a mixed population is going to be the probability they meet another hawk conditional on being a hawk. Which is, later lectures, this will be a very important expression, but today it will be boring, okay? But I just wanted to think through that. You're a hawk again, you're in a mixed population, there are processes that determine encounters with other individuals, so we're going to want to write some expression for that biologically that has to do with assortment, how individuals meet competitors, okay? But for now, I'm just going to have it be a placeholder. We're just going to say probability of hawk conditional on hawk. Good? Right? I'm going to write the structure of the expression times the fitness consequences of when you're a hawk meeting a hawk. This is just totally abstract. This is a definition of how we make models, how we write fitness expressions in evolutionary game theory. Plus the probability you meet a dove when you're a hawk. Yeah, so the probability you meet a dove conditional on being a hawk. Yeah. If that happens, you get the payoff of meeting a dove. This is just definition. This would be true of any model of this structure. Yeah, but now we're going to put the expressions in. But it's good to know the structure. Yeah, this is the idea. So this is an average, right? So this is the probability you get this payoff, and this is the probability you get this payoff. There could be other strategies in the population, and then this expression would be longer. It'd have more terms in the average, but this is just an average. Okay, so the probability you meet a hawk conditional on being a hawk in this model is little p, which is the frequency of hawks. We assume it's a large population. So the fact that you're a hawk doesn't reduce the number of hawks you can meet, right? If it was a small population, it would. You'd have to take yourself out of the random assortment process, but we'll assume it's a big population. We can ignore that. So this is just P times what a hawk gets when they meet a hawk, which is just that. Good? Plus the chance you meet a dove, which is 1 minus P, just the rest of the time. Yeah? Is it good? You could make a symbol for dove, like Q, but it'll just be 1 minus P. Yeah, so there's no point in making the algebra harder by adding extra variables, is there? And when that happens, happy days, right? You get V. It's the whole point of being a hawk, really, is that experience. Yeah. Good?
I have a question, sorry.
Yes.
So the probability is the second one. So it is a being a dove. In what context?
This is the social interaction. So there's some process by which individuals end up being paired up to contest this resource. And I'm summarizing some rich mechanistic model of assortment into this probability type. And when I put P here for it, that means it's random with respect to this locus. So whatever it is about being a hawk or a dove has no influence on which individuals end up meeting. Yeah, and this model doesn't have anything like assortment by genotype in it. In later lectures, we will do kin selection and inclusive fitness, and then we're going to do a lot with this expression, a whole lot. Yeah, but for now, I'm going to ignore all that. And okay, so what good is this, writing this expression? We're not done yet. Okay, now we have to do the same thing for doves. So, but we've made progress. So the idea is we want to compare in this mixed population on the right of the board, in here internally, we're at some value of p, any value of p. So I'm writing an expression that says for any value of p, what's the average fitness of hawk? And that's what I've written so far. I'm going to do the same thing now for dove. And then I'm going to be able to say, when are those the same? And that's going to give me the point in here where evolution doesn't move. Okay? So now we do the same thing for doves. I'm going to rewrite this structure. Yeah, just so you understand. The probability you meet a hawk conditional on being a dove. That's bad, right, from the dove's perspective. Yeah, but it happens. Times the payoff to the dove when they meet a hawk, plus the probability of meeting a dove conditional on being a dove, times the payoff to a dove when they meet a dove. It's symmetric with the previous one. Yeah, you just swap the labels. The difference comes when we put the model into it. Yeah? Questions? Does this make some sense? Okay, I'll walk it through again. So this is the average fitness of doves. So you want to picture there's a bunch of doves in the population. If we knew which individuals were doves through some mass surveillance genotyping project, we could measure the fitness of each of them and then compute the average fitness for the dove allele. And that's what determines the evolutionary dynamics in these models, where you don't have drift and population structure and all the other fancy things. We just want to know what natural selection would do. That's the thing to calculate, and that's what we're writing down. So that means we need to know what proportion of all the doves meet hawks, and that's what this probability is going to give us. And we need to know the proportion of those doves that meet other doves, and that's what this probability gets us. And then these are the consequences in those circumstances. And so across a bunch of doves, this is the expression for the average change in fitness. Good? And now we put it in. So again, the probability you meet a hawk conditional on being a dove is just going to be p again, because there's no assortment by genotype. Being a dove doesn't change who you meet. All that matters is how common hawks are. And when you meet a hawk, you get nothing. Yeah? Which makes the math really easy. But just some advice as someone who makes models sometimes for a living, set some consequence to 0. It really does magic for the algebra. You want to cancel terms. Without loss of generality, usually you can set something to 0, and then great things will happen in your expressions. Classic strategy. Okay, so the rest of the time they meet doves, and then they get v over 2, which is the dove-dove payoff. Remember? Because they both display, one gets tired and leaves first. So half the time you get v, half the time you get 0. Good? Right. Now, we can ask, when these two things are equal, or is there a value of p, the frequency of hawks, under which the average fitness of hawks and the average fitness of doves is the same? And we're asking that question because we're looking for this point, which is implied by v less than c world. Rare doves increase, rare hawks increase, somewhere in the middle they meet. Is there a value of p where selection is effectively neutral? Or balanced would be a better thing to say, maybe, that it's balanced. So we ask that question just by equating these two things. Yeah? This is progress. Right? So this is an equation, so I'll make the equal easier to see, that is asking the question, where is this equilibrium? And we're going to solve that expression for p because we want to know the location on this line segment where selection is neutral. Because that's a destination for the population. Yeah, that's where it's got to end up. So again, for those of you who love algebra, for the algebra lovers in the crowd, right? The fun thing about algebra, and by teaching topics like this to brilliant PhD students from many backgrounds, all of whom are capable of doing algebra but have forgotten that they are capable. It's an unfortunate thing about algebra is that there are a very large number of ways to get the right answer. And so you can start off with a terrible tactic and go lots of ways, but you'll get there eventually, and that's totally fine. And I just say this because I'm going to do my style, but there are other styles that are fine. When it comes to doing algebra, just obey the rules and eventually you get there. That said, in the homework problems, I've seen many times that I will think it's an easy homework problem because I solved it in like half a page, but then students bring me like 8 pages of algebra and it's correct. Yeah, exactly. Exactly. Yeah, Christine, it's a good analogy for algorithms. There's a bunch of algorithms which will compute the same thing, but some of them are terrible. In fact, most of them, right? And so if you pick a terrible algebra path, but you get the right answer, that's perfect. It's just great at this point. Don't worry about it. Totally fine. I'm going to get rid of the 2's because I hate them. Right? No, factors of 2 are a curse in PopGen, the population genesis. Know what I mean? You're always off by a factor of 2 somewhere in your answers. It's just terrible. And so we hate 2's and we always get rid of them as quickly as possible. No, you can't purge them completely, but we don't like fractions. So we're going to multiply both sides by 2. PV minus C, 1 minus P, 2V is equal to 1 minus PV. I want to get everything that has multiplied by P together because I'm going to isolate P. So we've got V minus C P's, there's minus 2V P's there, plus 2V, and then over here we've got V minus PV. I'm going to start combining things, if I got this right. Yeah. Wait, did I do something wrong already? No? Okay. Yeah, so we've got V minus C minus 2V. We got to bring this V over. Yeah, am I cheating? I've magically teleported something from the right-hand side. And I'm going to take this one over here. So it's V minus 2V. And then we start simplifying. So we've got 2 V's and we've got minus 2 V's. So all of those go away. Oh, isn't that great? I just love it when it works out like that. And then over here, this is minus V, right? This becomes minus V because we've got minus 2 V's. So we've got P minus C is equal to minus V, or P equals V over C. Yeah? All right, good. So I've noticed many times as I've derived this model, there's this scientifically documented phenomenon called blackboard radiation. The closer you are to a blackboard, the dumber you get, right? So it's like sometimes I get lost in like basic algebra that I'm teaching to my son at home, right? But this happens. So if you spot a mistake, you should gesticulate wildly and rescue me from it. But it's true, it's closer you stand, right? It's kind of radiation. Does this make sense, what I did? It's just boring algebra. The expression is interesting, though, because now we've got this point where P equals V over C, and that's the location of our internal equilibrium. So interpret the expressions. First thing we want to do. We say, well, this is only internal to this line segment between 0 and 1 when V is less than C, which is the condition for the equilibrium to exist. As V increases, this gets larger. At the point at which V equals C, you're right here on all Hawk world. Yeah, so you can see the connection, right? So it's sort of like this equilibrium always exists, but up here it's like it's outside of the range of possible frequencies. Yeah, this does a lot of violence to the evolutionary dynamics, but mathematically it makes sense. Yeah, good? As V gets smaller, or the relative cost of regression gets bigger, yeah, because you can make C larger as well, this gets smaller, it approaches 0. Yeah, so in principle, if V got small enough, you could get an almost all dove world. Yeah.
I'm sorry, Richard, maybe that's a silly question from my side now, but I don't have this case so much in my analysis. If there is no other strategy to evade, if you do the first step of analysis, if a mutant strategy can evade somehow, can you actually skip to search for internal equilibrium of internal frequencies, or does this depend always on initial condition? Also, is it possible?
Yeah.
To say it the other way around, is it possible that you have that your strategies cannot be invaded, but nonetheless there is
An internal. Yes.
equilibria if you have
Yes.
if you have another initial condition.
Yes, you could. I mean, there's an even simpler situation where your question is super important. You can have two strategies which are both ESSs, and then there will be an internal equilibrium, but it will have the opposite nature of this one. So in this one, the internal equilibrium is an attractor. It's a candidate for where evolution takes the population. Because
This is Bayesian of attraction.
yeah, it's a Bayesian of attraction. When if hawk and dove were always ESSs, there would also be an internal fissure somewhere in here, but it isn't, and it's technically in equilibrium mathematically, and you would derive it the same way. We'll have a model later that's like this. But evolution would take you away from it as soon as you were perturbed slightly off of it. And if you were perturbed on the upper end, you'd run to one system, and if you turned to the lower end, you'd run to the other. And those bifurcating equilibria happen in lots of models too, and we'll have one, I think, next week. I mean, yeah, on Monday's lecture, I think we get one. Or actually, no, we're going to have one now. Oh, yes. Oh, happy day. We've got time. We got like 20 minutes. I'm going to give you one now. Yes, I'm going to do Retaliator. Retaliator has one of these.
This applies to.
Yep. Yep. Okay. I can erase this? Yeah? Beautiful algebra? Yeah? Yeah. All right. The algebra is not exciting right now, but the algebra is never exciting, to be honest. But the translation of biological details into these expressions gets more fun as the lectures go on, at least for me. And I hope to bring some of that fun to you as well. By like lecture 4, we're doing statistical genetics up here, right? We'll have covariances, and I'm going to be having lots of fun. I have fun, you'll see. I really enjoy myself, and I hope you do too. But we got to start here so I can build you up to like what's a phenotype-genotype covariance, right? But that's where we're going by lecture 4, I think. Okay, I want to spend the last 20 minutes today extending this model to include a third strategy, which a large number of people intuit is that the problem with this strategy, with this model, is that there's no retaliation. You want to have a version of dove which fights back. It's willing to get along. It chooses to display and resolve its differences without violence, but if it's attacked, then it will fight and defend itself. And this strategy is usually called Retaliator in the literature. Retaliator. Retaliator acts like dove, but fights hawk. So let's redraw the payoff matrix for this game now for 3 strategies: hawk, dove, and retaliator. Okay, so the hawk, dove, I'm going to put retaliator on this. The hawk-dove matrix we can do real quick. I'm going to do it fast, and I'm confident you will understand what's going on. So hawk is v minus e over 2. Hawk against dove gets v. Dove against hawk gets 0. Dove against dove gets v over 2. Now let's think through retaliator. You are retaliator. Yeah, you're nice, but you're tough. No one pushes you around. Yeah? So you meet a hawk. You don't know they're a hawk. You're not genotyping them. You know them from their behavior. So you start out like, hey, let's wrestle. We both want this, let's just wrestle. And then the hawk attacks you, and you're like, oh, it's on. Right? So people still say that? Sorry, but whatever people say these days when a fight is about to happen. So you get the hawk-hawk payoff because you act like a hawk. Retaliator is basically a mirror of the strategy, the behavioral strategy its opponent uses. So you end up getting the hawk-hawk payoff because you fight back. And it's and the V's and C's apply to everybody, regardless of their genotypes. Does that make sense?
But we also have switcher, no?
What's that?
The switch, whichever strategy.
Yeah. So we'll fill in the rest, and exactly, it'll switch. So Retaliator meets Dove. It acts like a dove because it says, let's wrestle. The dove is like, I love wrestling. And then they wrestle. And somebody wins. And so it's V/2. Retaliator against Retaliator. They both like wrestling. So it's just like two doves meet. Again, it's V/2. The flip side, now Retaliator's not the focal, but if you're a hawk and you meet a Retaliator, it's just like meeting a hawk. And if you're a dove and you meet a Retaliator, it's just like meeting a dove. You never know, in fact, that they're a Retaliator. You don't discover it because you don't provoke them. Does this make sense? So, congratulations, you have extended the world's stupidest game theory model to something slightly less stupid. But this is progress. You have to incrementally do it so that you build up your intuitions about how it works. And now I'm going to take you in a more in a faster progression through asking what the evolutionary consequences are of adding Retaliator. And it's going to be easier to do that if I draw a big triangle on the board. So what I mean a big triangle. On the bottom of this triangle, I'm going to draw the line segment that we had before. So the bottom of this triangle is P. It's the frequency of hawk in the population. So if we're on this line on the bottom of the triangle, we're in the model that we already derived, the basic hawk-dove model. And we know, let's assume V is less than C, as it makes the model interesting. Yeah, for the moment. And when that's true, hawks increase when rare, doves increase when rare, and there's some internal equilibrium at V/C, where local evolutionary dynamics move you back to that point, to that mix. This could be 2/3, right? If V is 2 and C is 3, then the mix will be 2/3. Yeah, 2/3 hawks, 1/3 dove. Good, that's the previous model. Now I'm gonna put Retaliator in this model. And this creates 2 more line segments, 2 more perfect models where we can exclude one of the 3, but also a big mix internally of what can happen. So the model is, the complexity of these models escalates pretty quickly. But in this case, we've got all the tools already to analyze this. So let's think about what happens when Retaliator is common. I can probably just talk you through this by looking at the matrix over here. So is Retaliator ever an ESS? Let's start there. Maybe it's a stupid strategy. Maybe we can just ignore it because it can't be an ESS. Yeah, it just gets invaded all the time. So let's ask, when Retaliator is common, what is it getting as a payoff? It's getting the payoff to itself. It's getting V/2. Yeah? So the condition for it to be an ESS is going to be V/2 is greater than the fitness of this rare invader. So let's consider hawk as a rare invader. A rare hawk is going to get V-C/2 because everybody in the population is a Retaliator, right? So it's like invading a population of hawks. Remember, a hawk doesn't get along with itself. We can do some algebra here, but probably you can tell that this will not be satisfied, yeah, because if there's any cost. Yeah. If you like being injured, then this can be satisfied for you as a hawk, right? Masochist would invade. But yeah, does that make sense? So Retaliator is an ESS against hawk. Yeah? Because it's getting along with itself. It's doing that thing hawk can't do. Is it, let's say R is ESS versus hawk. Is it also an ESS against dove? So local evolutionary dynamics here on this line segment, you move up. That's the ESS, yeah? If you're in the neighborhood of it. What about dove? So retaliator will be an ESS against dove when V over 2 is greater than what the rare dove gets. What's the rare dove get?
V over 2.
V over 2, thank you. Interesting algebraic question. Yeah. So natural selection doesn't care what happens there. A rare dove in a population of retaliators behaves just like a retaliator. From the consequences that we have in the model, that is the consequences of the interaction, there's no fitness difference between these types. You could rescue this by saying, oh, there's some developmental or mechanistic cost to retaliator because it's fancy. It's got to pay attention to things, and that's a fitness cost. You could do that, but you're assuming a consequence, right? And I'm not against that, but because that's learning what would be required in the model to create a fitness difference, to make retaliator an ESS. But I'm not going to do that today. I'm going to let you just dream about it or do it in your free time. Instead, we're going to ask what happens if selection is, and this is, Christine, this was your question, I think, before, there's a whole region here. In fact, this whole line segment is evolutionarily neutral. Any mix of retaliators and doves is selectively neutral. Evolution doesn't care about the mix. It won't tend to increase or decrease as long as you're on this left line segment. Does that make sense? Yeah, I'm going to let the
Actually, I'm sorry, this was actually not my question.
Oh, sorry.
My question was more like, as here we always have the case that dove and hawk is not stable, right? So this means another strategy can invade. And here also, dove can invade retaliators. My question was, if this is a stable strategy in the sense that not another strategy can invade, is there nonetheless a possibility that there is an internal equilibrium if we change the initial condition, if the starting point is a different one? But it doesn't matter now for this.
I think I asked you, not in this model, but I think I understand what you're asking. Yeah.
It doesn't matter now. But
yeah, okay.
It's really interesting because now we see a case of neutral drift.
Yeah.
But it's a question from before.
Yeah, okay, I understand. There's going to be, there'll be something here that's not what you asked, but yeah, I understand what you're saying now. In this model, no, what you asked could not happen for reasons that have to do with the polynomial form of the replicator dynamics, but we can talk about it some other time, but we'll talk about this in later lecture. Okay, let me come back to this. This is an exciting thing in a model. You have found someplace this whole line segment where the model has no idea what's going to happen. That's what you want to read this as. Unmodeled forces will determine evolution dynamics there. Drift, migration, mutation, right? There's no reason to assume mutation is symmetric for these strategies. You can assume any mutational architecture you want. Go crazy once you start thinking about genetic architectures. But in evolutionary game theory, we start by taking all of the real biology away and just saying, if natural selection got its way, what would it do? And this is not a problem with the model. It's giving you the answer to the question you asked. But maybe you didn't think you asked it. Well, I asked it. I've led you into this forest. But, but you know what I mean. So the important thing is to understand why the model produces it. And it produces it because retaliators look just like doves in this model when they only meet doves. Yeah. But I think I have just enough time for this. There are then two questions for us to ask. Okay, so rare retaliators can also increase. So if you're down here on this end, hawk is not an ESS against retaliator, or it is. A rare retaliator just ends up fighting all the hawks, and so it's neutral. But if there's a small number of retaliators, I'm not going to demonstrate this to you mathematically. I'm going to wave my hands. It's a form of proof, right? If you have a small number of retaliators and they occasionally meet one another, they can invade a population of hawks. It's because when they meet one another, they get the dove-dove payoff. Yeah. So selection is incredibly weak down here, but it can very gradually increase the frequency of retaliators. So this whole line segment is dynamics taking you to a retaliator world. Now we want to ask what happens on this edge when we add a hawk I, because I want to show you something. And we want to know what happens here when we add a retaliator. Right, so retaliator can be an ESS against Hawk. Can it invade? If it invades, it's going to have to invade this point. Right, so we need to ask what happens there. And I want to show you how to answer questions like that using the same tools that we had before. So first we figure out when we're at P equals V over C at this point, what is the average fitness of a hawk or a dove? They're going to be getting the same average fitness. That's the definition of the equilibrium, but what is the expression for that? And we can very easily do that by just writing down the average fitness of dove when there's a mix. And remember, it's 1 minus P V over 2. I chose the simplest one. I'll remind you why. Because 1 minus P of the time you meet another dove, and then you get the dove-dove payoff. P of the time you get 0. So I don't have to write it. Yeah? Told you, I like zeros. They're very nice. Okay. Now, we know P, so we just substitute it in. Yeah? And so this becomes 1 minus V over C V over 2. And you say, what is that? That's the expected fitness of a dove or a hawk at this internal equilibrium. This is what an invading retaliator must beat. Yeah, so what does the invading retaliator get? So the condition, for retaliator to invade, we need 1 minus V over C V over 2, B over 1 minus V over C V over 2 to be less than whatever it is the rare retaliator gets, which we can figure out. We know how often it meets a hawk. It meets a hawk V over C of the time, right? Because that's the frequency of hawks at the mixed equilibrium. So V over C of the time, the retaliator gets V minus C over 2 because it meets a hawk. You with me? Now remember, the notes I've given you on the website have this as in a slow motion derivation, but I'm just trying to pump your intuition right now and keep you moving. 1 minus V over C at the time the retaliator meets a dove. It doesn't meet another retaliator. He's the first retaliator in the world. Yeah? So, and then gets the dove payoff. Now, you could do some algebra here. Or you could just pause and take your eyes and scan the equation. And I want you to notice that this term and this term resemble one another. Yeah? And again, you could just brute force algebra this, but this is one of these cases where your eyeballs can do all the work for you. Yeah, okay. So the only difference between these two expressions is this thing, and this term is negative, because V is less than C. Yeah? This term is negative, and it's the only thing that differentiates their fitnesses. And so the rare retaliator always has lower fitness than hawks and doves at the mixed equilibrium, which is super weird. Yeah? The reason is it fights too much. Hawks and doves have already figured out the optimal amount of fighting, and they're at an equilibrium for it. Retaliator comes in and it's maladapted to that amount of fighting, and it fights too much. Yeah? It should give up in the presence of hawks, like the doves do. Then it'd have the optimal dove fitness, but it gets into fights all the time. Yeah, so it actually does worse. It can't invade. It's too fighty. We all have that friend, right? A couple drinks, right? So this is retaliator. When it's rare, it can't deterministically invade this equilibrium. Local dynamics take you right back to it. Awful, isn't it? Awful world. Again, stupid models, but they reveal things that you can't get intuitively, and then you have to think through what it is in the model that produces that dynamic, and what was it in our intuitions that was wrong before, and how do we repair that so that we can generalize to real cases. That's what I think of as the point of this kind of applied math. One more thing, and I've got time to do it, is to think about what happens here. So, if retaliator, now we're going to say there's going to be a rare hawk, and we're going to introduce them on any point along this line segment. And I'm going to let the frequency of retaliator be Q. All right? Just the frequency of retaliator. So when Q is 1, we're up here, and when Q is 0, we're down here. So now we have two frequencies, P and Q, that determine where we are in this triangle. And what I want to do first intuitively for you and then prove is that there is going to be some value of Q along this line, where on one side of it, the evolution dynamics are different than on the other side, even though every point on this line is neutral. And that's because when we add a rare hawk, if Q is small, hawk can increase. And I'll prove this to you in a moment. Why? Because there are lots of doves. When Q is small, you're down here. Say the point is here, just for sake of discussion. I'll derive an expression for it. If you're below it, there's lots of doves, and doves are food for hawks. So the rare hawk comes in, and there's lots to eat, and they do well. They don't want to meet Retaliator, right? But the Retaliator is rare when you're down here. So dynamics below this will take you that. Yeah, does that make sense? And there's going to be some division. And if I had another hour, I would derive this line for you, and we would have lots of fun. Yeah, but if we're above this, the opposite thing happens. Now you've got enough Retaliator in the population to hurt the rare hawks. And so evolution dynamics up here tend to take you back to the line. And then you drift around again. All these forces we haven't modeled, and maybe you drift down here and then you end up there again. We can't say. This model doesn't have those dynamics in it. But it does have enough richness to show us that that's a possibility if other things happened. How would you derive this point? It's the last thing I'll do before I let you go.
Sorry, can you one more time say what happens when you have a lot of retaliators?
Yes. When there's a lot of retaliators, a rare hawk has a sufficiently high probability of meeting a retaliator that they get into a fight, and then that's bad. They get injured, and so they'll have lower fitness than V over 2. Because remember, retaliators and doves along this whole line are getting V over 2. That's what you have to beat. If there's a lot of retaliators, hawks don't get V often enough, and so their fitness is lower than the average. So this is the point at which you could say this line segment is stable against invasion by rare hawks, and below it, the line segment is unstable against invasion by rare hawks. So in that case, you'll end up here. In this case, you go back here to this line. And we can derive that point, right? We can say, we know that what's the condition for some mix of retaliators and doves to be in ESS? Well, we know they're getting V over 2 anywhere along that line segment, so that's what you got to beat, right? Because it's just like a bunch of doves interacting. They get V over 2, yeah? But the rare hawk, what do they get? Well, there's some value Q that we're going to use. So it's a rare hawk. They don't meet other hawks, but Q of the time they meet a retaliator. When they meet a retaliator, they get V minus C over 2. And 1 minus Q of the time, they get V, because they meet a dove. So this is where the intuition comes, right? So if Q is small, you're down in this region, and then this term dominates, they get V more often, and that helps the rare hawk invade. If Q is large, this term dominates, and it increases, yeah? And I'm at 1 minute, so I'm gonna skip the algebra, but it's in the notes. I'm gonna skip the algebra, but I gotta do it in my head real quick. Yeah, so Q is less than V over V plus C, right? And that's this point. And there's nothing magical about that expression, but you can just think it through. If V is 2 and C is 3, then this is 2/5. And it's just the point where the costs are equalized. But you can analyze what happens when you change the parameters. So if you make V larger, it increases, yeah? If the value of the resource is bigger, the threshold, the Q is the frequency of retaliators you need to keep hawk out. Think of it that way. I'll say it again. This value of Q, V over V plus C, is the frequency of retaliators, the minimum that you need to keep hawks out of the population. Yeah, it's your defense quota. Yeah, you need that proportion of volunteers to get into fights with rare invading hawks. Yeah, remember, it's costly for the retaliators to do these fights, which is something we're not modeling. But you might think if they could choose, they'd rather you did it. Yeah, and that's next week. But so if V increases, this is a larger expression because if V is large, that benefits hawks. Because every time they do meet a dove, they get an even bigger payoff. It's the bonanza. So if you increase the value of the resource, you need more and more of these retaliator guards in the population. Does that make sense? Yeah, that's the sort of comparative statics. Okay, I want to stop here. It's been an hour and a half, and I will lose my voice. No. Hopefully that was clear. Take a look at the website, which I accidentally erased. Did you get the URL?
Yeah.
Yeah? Okay. If you didn't get it, somebody else has it or come up to me. There's one homework problem that I've posted. If you go to the repository and you scroll down, I've got all the homework problems listed. If you miss a week, we're recording these, you can catch up. You can do the homeworks at whatever pace you like. Okay? As long as you turn in solution sets to all of them, 6 months from now, I can give you course credit. Yeah, as I know life is complicated. My life is complicated too. Yeah, so if you miss a week or you fall behind on the homework, that's fine. I structure the lectures so you still get stuff out of them even if you haven't done the homeworks. That said, it's good to look at the homework and make a little attempt before the next lecture because I try to build them, okay? With that, I thank you very much sincerely for your attention, and I will see you on Monday for the next lecture. Okay.